Hey there, everyone. Ryan Schul here. This is my channel, Straight Data Science. Welcome to the channel if this is your first time coming, and welcome back if you've been here before. So today I want to show you a concept that I kind of touched on just a little bit before in the past. I have a video based on this, but I tried a different approach this time, and I think the outcome is really, really cool, probably even better than what I was able to achieve in the first iteration. And it was kind of different too. I don't like to be redundant and repetitive and do the same thing over and over. So this is a different approach, different angle, different perspective. But basically, I want to show you how to use a calibrated classifier um, to go ahead and predict crime. We're going to try to forecast the probability of a crime occurring and what type of crime and where it's going to be, given the latitude and longitude coordinates around New York City and the time of the day as well. Now, I'll give you a spoiler alert right at the beginning here. You can't predict an incident of crime with 100% accuracy, okay? It just doesn't happen. Crime is mostly random, spur of the moment. Some of it is premeditated. We can't predict what people are going to do. You can't read people's minds, okay? So it's not going to be like that. But based on historical events, you can take density estimates and sort of like a clustering technique. It's a little bit different. I'll get into that in just a bit. But you can predict with a certain degree of accuracy where and when a crime will occur based on historical events. And I can tell you from experience, some neighborhoods are more subjected to violent crimes or high incidence of crimes, and some neighborhoods in New York City are basically crime-free. Where I live in Long Island City, it's not a high crime area at all. There's not a lot of police that patrol the area, practically none, to be honest. And it's white collar, mostly demographic, pretty affluent, and we really don't experience a lot of crime. There are random incidents, to be sure, but it's not a high crime area. There are places you can go in the Bronx. You won't go in the Bronx without a battalion guarding you, right? Like you just don't go to some places, right? So given historical events, we can try to model out or anticipate where crime is going to occur, and then the time of the day of the week, and then the actual event, the crime event as it's labeled or as it's defined too. So there's a bunch of reasons why we might want to do this, right? To deploy patrols more efficiently, increase visibility and potential hotspots, prevent crime proactively, right? Also, we have to be careful to avoid bias. We have to understand urban and planning policies, right? There's a lot of politics behind this, right? A lot of legislation that drives this. But if we can, give better information to city planners and try to forecast crime more effectively, more efficiently, we can utilize our resources more effectively and efficiently too, okay? So that is the goal here. And there are certain temporal patterns. Temporal means time-based, right? So based on the time of the day of the week, even weather-driven events, parades and sports events, things like this, that can determine crime or that can drive crime rates, right? We can model the probabilities of certain crimes occurring, okay? We can't say with absolute certainty there will be a crime and there will not be a crime. We can't be 100% accurate or say there's going to be zero crime here again, but we can model this based on probabilities, okay? So maybe there's a 14% chance of a crime occurring on a specific day at a specific time. Maybe there's a 90% chance, 91% chance of a crime occurring on a given day, given a certain time, okay? So that's what we're going to try to achieve here. The model that I came up with is called CalibratedClassifierCV. CV is a cross-validation technique to avoid overfitting during the calibration process. There's a few different ways to handle this problem. You can use a random forest classifier, which I used initially, and I found the results to be less than desirable. I was getting a lot of very high crime rates, like 98, 99%. I'm scratching my head thinking, like, I don't think you can be 99% accurate predicting these crimes. And I saw a lot around, I think it was 14 or 16%. And it's tended to go into those two buckets. So I think the classifier was getting confused and it just wasn't really learning the nuances and the patterns of the data well enough to make those forecasts. So I got away from that. I ended up using a calibrated classifier CV, again, cross-validation. And I tried a log regression classifier. So it sounds like regression, right? Log regression sounds like regressor. It's actually a classifier. I think it uses continuous variables for the regression, but then maps everything to a classification system. I think that's why it's actually a classifier, but it has a name like a regressor. Anyways, these things are pretty interesting. They tend to be log normal, and it sort of made sense when I first tested the model, and I got some pretty good results. The tail can be wide and kind of fat. That could indicate a lot of crime in certain areas, given the time of day, given the day of the week. And you can never have negative crime. It can't go below zero, right? You could have zero crime, you could have 100% crime, can't go below zero. So the log regressor, initially I thought was going to be pretty good, but then I steered away from that because I saw some shortcomings over there. So I ended up going with calibrated classifier, and I'll show you why in just a minute. So here's the code. I'm going to go ahead and import a bunch of libraries to help me with the analysis. I can go ahead and now this is all linked together now. I had it kind of separate. I'm not going to run this because it takes an extraordinarily long time to run, probably 25 minutes to run. It could have been even longer. I ran a couple of versions of this and it kind of dragged on and on. It did finish, but I'm not going to run it here. It's just going to take too long. Okay, but I'll just walk you through the code and what it's doing. So we get this data right here. It comes from NYP arrest data year to date. And if I open this file, I can show you what it looks like. This is sitting on my desktop, and I have a link to the file at the bottom of this Jupyter notebook down here. And I never figured out why this thing can't just go to the end. It always has to skip to the end, and then it doesn't go to the end. So, and then it doesn't even go down. Okay, so that's annoying. I'm going to refresh the whole thing. It's obviously in a mood. This computer gets into a mood sometimes and just doesn't do what I ask it to do. I don't know why, but anyways, I'm going to override the computer. I'm in charge here, not the machine. So let me just go ahead and tell this thing what to do. Okay, and go down. Okay, now so I'm in control again. So the data source comes from here. You can take a look, Control C, Control V to paste it over here. This is the link. And this comes from New York City. And I'll tell you, I've done some analysis on some of these data sets, probably at this point, 10 to 12. These links go dead for a while. After a while, I don't know why. So grab the data while you can. If you can't find this exact data set, you can look around for something similar. We're using a few different columns here, not everything. You would need latitude and longitude coordinates, so you can get those over here. You would need things like the description of the crime and then the date. And we don't even get into like number of arrests or age or male or female. There's nothing gender related here. There's no biases with the data. So I feel confident with that. There was one thing I wish they had in the data. They didn't have the time. They give you the date. So Monday, Tuesday, Wednesday, whatever the date is. There was no time of the arrest. So that was unfortunate. I think time does play a lot into the crime, like the occurrence of crime. You don't see a whole lot of crimes occurring at 8 a.m., 9 o'clock in the morning. A lot of people are heading to work, or maybe if you work third shift, you're sleeping. You don't see a lot of crimes at that time. Most of the crime is like evening time, 6, 7, 8, 9, 10, midnight, overnight, early hours, 1 o'clock, 2 o'clock, 3 o'clock in the morning. So without that time element, I had to create my own time, and they tried to make it very realistic and plausible and believable. So I think this is going to work. I wish they did give you the time, but they didn't. I'm a big fan of like, you know what? If I don't have the data that I need, I will still get the job done. I'll figure out how to get it done. I will manufacture some data, make it realistic, and deliver a final product. I've worked with people that they look at the data and say, well, we don't have the data, so I'm not doing anything, right? And months go by and you're talking to the person, well, where's the report I asked for? And they're not doing it because their excuse is, well, we don't have the data. Well, get as close as you can. Do whatever you can, right? If you have everything you're missing time, create some times that should be plausible and realistic, right? And get the result, get the job done. Don't just sit there for months on end and wait for something to happen that is never going to happen. Okay, so not a big fan of that, but I've worked with a lot of people. They take that approach, right? Doing nothing. So here's the data set. This is what it looks like. Okay, that's what I'm going to, no, not sure what that is. That's what I'm going to feed into my data frame. So we get the data. We have one thing here. We're doing reverse geocoding to get the address based on the the latitude and the longitude of these coordinates, right? So we have the latitude, we have the longitude. We can do reverse geocoding to get the address, the neighborhood, the suburb, and the city district. So if you do geocoding, you can get the latitude and longitude from the neighborhood, the address, suburb, city district, things like that, right? Reverse geocoding is just the opposite. We have the lats and the longs. We're getting the details of the neighborhood addresses and things like that, okay? So that's one thing that causes this to go pretty slow. You have to make a bunch of calls to geolocator. This is a Python library that gives you this data for free, but it's pretty slow, right? And it's going to take a while. So that part slows it down. I did get the rest date, and I tried to get the hour. These are all zeros, so I actually manufactured some hours. It's going to be about midnight to, I think, 3 or 4 in the a.m. in the morning. That's when a lot of crime events tend to occur. Weather is going to play a factor too. Event density is going to be pretty huge, and then social sentiment. So these are things like, is there some kind of discussion on Facebook about maybe a small gang committing some crimes or something like that? Like if you're getting a lot of momentum online, and then you take your discussion from online to offline and actually commit the crime, that could be another factor to consider here, right? So again, I can't run the code. It's just going to take too long, but I'm just talking you through it. So we have the latitude, longitude, try to derive the hour. We don't actually get the hour from the data, so I'm going to go ahead and make it. And then I'm going to try to map the boroughs. So we have Bronx, Manhattan, Queens, Staten Island, based on, again, the latitude, longitude coordinates. We're reverse geocoding to get all these details, right? So this is called data engineering. So if you have some data in your feature set, that can help you create new features from your existing features. This is feature engineering. You're engineering brand new features. I don't have the borough mapping. I don't have Brooklyn, Bronx, Manhattan, Queens, or Staten Island. I don't have the neighborhoods. I don't have things like neighborhood, suburb, city, district. I don't have that. But based on latitude, longitude coordinates, I can manufacture that, right? I can create that. So we're building up all these features, right, from the existing features, getting the neighborhood. The arrest date, we have the day of the week. We can get that from the date. The crime type is going to be from the crime description. And I'm getting about, whatever this is, 25 or 30 latitude, longitude coordinates. I found this online for major NYPD precincts. So this is the lat long coordinates for the precinct. This makes it easier to correlate enforcement presence, or cooperate between jurisdictions, or understand if there's gaps in jurisdictions, right? So I don't think major crimes are occurring directly outside of an NYPD precinct, right? But if there's gaps between precincts, right, and there's not a lot of coverage in this area, that could be a hotspot for crime. If there's overlap, there's probably going to be less crime committed in that area, right? So I want to take all this information, the feature engineering elements I just created or just mentioned to you, and enter the precinct coordinates so we can see, are there gaps, or do we have good coverage here, okay? To get the distance between the precincts and to map this, I'm going to use the Habersign concept. So Habersign looks at the latitude, longitude coordinates and makes a prediction of distance based on not how the crow flies, but based on like the curvature of the Earth, sort of. So you can Google that, look that up if you have any questions about that. We use this for, and this, I think this is in terms of radians, or what was it? What would it be? Meters or something like that. Now I have to look up. Now I'm interested in the SW Habersign. Sometimes I go off these tangents. You guys know that. So Habersign is a formula used to calculate great circle distances between 2 points on a spherical surface. Okay, so that's what it is. Based on the curvature of the Earth, we can map out different distances and find the distance between these two coordinates, right? So that's what Habersign is great for. Once you have the latitude, longitude coordinates, you can find the distance between those coordinates, okay? So hopefully that makes sense. And one other thing that makes this kind of slow is that we're using KDE. So this is kernel density estimate. We are using this technique basically to help us to understand crime intensity at a location based on surrounding points. So a naive way to set this up is just to take the crime counts. So how many counts do you have given a certain latitude, longitude coordinate, or looking at the Habersign distance between a couple of points, right? In like whatever, like a quarter mile square radius or something, how many crimes are committed there, and then move over to another slightly different jurisdiction within a quarter mile radius, like how many crimes are committed there. That's one way to do it. It's a little bit naive, but you can count all the crimes in that area and come up with an estimate, right? The kernel density estimate has kind of a different approach. It looks like all the surrounding data points and takes an intensity based on the density of occurrences in that area. So it's like a smooth heat map density score rather than just raw counts of crimes. Okay, so it's a little bit more articulate, it's a little bit more refined to help us understand the concentration of crimes in certain areas. Okay, we look at the density surface, it's like a probability that crime could occur there rather than just say, okay, there was 5 crimes of larceny and 4 violent crimes or something like that. So the KDE approach is going to help us come up with a more sophisticated um, um, prediction of crimes that we're going to do in just a minute here. So this is what the original data looks like over here. Okay, on the end of this data frame, I am appending a few new columns. So I'm getting neighborhood, again, using the reverse geocoding technique to get the neighborhood from the latitude, longitude coordinates. Hour, in this case, is always 0. We got this from the data frame. And unfortunately, there's just no hour. All they have is date. That would be great if they had an hour of the rest. That would help a lot, but they don't. Okay, so again, we're going to make that up and make it accurate and very realistic. But like it just wasn't given to us, right? So I can't use what I don't have. We're going to look at the weather score, event density. This is KDE that I just mentioned. Social sentiment, so this can be talk or chatter on Facebook. Maybe we're going to go out and commit a crime and you're a member of a gang or something and they're talking about that, right? So that could lead to an actual crime event in the real world, take it off the online world in the 2D environment and bring it real life into a 3-dimensional environment. So we have borrowed day of the week, so we can get that from the date. Crime type, this is the definition or the description of the crime. Density to precinct kilometers, and then crime density. So these are the KDE things I just mentioned before, right? So we have crime density coming from the KDE score, given latitude, longitude, and distance to precinct is, again, based on the Hauer-Stein distance between the latitude and longitude of the spot where the crime occurred. We have the distance to precinct in terms of kilometers, okay? So that's the background. It's a lot of stuff. I know that. Hopefully that makes sense. So I'm going to go through in this data frame and loop through all the positions or all the points that have latitude and longitude, and it's not equal to 0. If you look closely, like some of these lat long coordinates are actually blank. Now they're filled in over here, which is nice. Here's the original data frame. But you can see here, sometimes it's just a 0, okay? So whatever event, the police report didn't fill those out, and it just doesn't include longitude, latitude coordinates. So if there's nothing there, again, we can't use what we don't have. We don't have it, so we can't use it. But let me see how many there are here. If I filter these out, hopefully not too many. Oh, okay, and the computer's going slow, of course, yeah. But let's take a second. Okay, so of course it's Excel, so it's wicked slow, right? Trying to count the zeros here. That's all I'm trying to do. Excel, please work with me. Please be kind. Okay. Okay, I'm not going to give up. I'm just going to wait for Excel to do whatever it needs to do. Okay. So, you believe that? It didn't even do it after all that. This is why I hardly use Excel anymore. It's like so unpredictable. You don't even know what is even going on. Oh, okay, I'm not going to give up. I'm not going to give up. I'm going to make it work. Okay, let me just do this. This is the opposite of what I want, but this is fine. Okay. So we have 57472, 57472 out of 71,242. So 57,000 out of 71,000. What is that, like 85%? Oh, and you need the equals. Yep, of course. 80%. So 80% of the records have lat long coordinates and 20% have missing lat long coordinates, okay? If it's not there, you can't use it. So I'm just going to filter these out. Based on that, I have this folium map right here. that has all the crimes and then the latitude, and longitude coordinate for each one. So if I zoom in, we can see this one here. This is Queens, criminal mischief. Okay. Here we have petite larceny and other state law. I'm not sure what that is. Over here we have vehicle and traffic law. Okay. Parking ticket or something. Grand larceny. That sounds pretty bad. And then vehicle and traffic law again, and maybe they hit rear end of the cop car or something, and a burglary. Okay. And you zoom in and you can see the details of the map. I love these Folium maps. This looks like this could probably be a doorman building. How you break it into a doorman building, I don't know. But anyway, so burglary was reported. Maybe that was an inside job. It looks like a pretty affluent part of the neighborhood. I don't think that should be occurring there, but in any event, that's what the record says. So yeah, we have the latitude, longitude coordinates. For each of these events. And just to be honest, guys, I wish I didn't have to narrate this. I do all this work 100% by myself. I would love to do all the research analysis, do all the coding, make it work, and give it to somebody else. Here's a handoff. You go talk about it. You go do it. Like, it's hard for me to talk. I don't know why. I grew up in Connecticut, but my voice doesn't work, and I just can't talk very well. So I get stuck doing this because no one else can do it. So that's it. And then I have this constant throat problem on top of that. So anyways, here's all the actual latitude, longitude coordinates for all the crimes in New York City based on that raw data file that I showed you, okay? So now we're going to take that data and use the KDE estimate, right? The kernel density estimate that we just looked at, and also the haversine distance to different police precincts. Again, assuming that there could be gaps in coverage between the beats of where these cops are going and where they're not covering, that would be the gap. So we're going to take all this information and feed it into the model and use latitude, longitude, hour, weather score, event density, that's what I just mentioned, social sentiment. So these could be posts on, Facebook, or maybe it's called Meta now. I'm not sure. That thing seems to change all the time. So if there's chatter about that, potential crime that could become an actual crime. So these are the types of things we're looking at. In terms of what else? So we have our weather score, event density, crime density. We start with 0, but then that's going to build up to a density based on a KDE estimate pretty quick. Day of week, neighborhood, and borough. And there was one more, HOUR. So I had to make up my own hour. So I'm looking at 2, 3, 4 o'clock in the morning. So these are my estimates. Again, I think a lot of crime occurs at that time of the day. It's so dark. A lot of people are sleeping. Perfect time to burglarize a house or, commit some kind of larceny or violent crime, right? In the middle of the day, when the sun is out and everything is exposed, you don't see as much crime, right? Overnight, under the cover of darkness, there's going to be a lot more crime. And again, we didn't have this in the original data set, so I can't report what I don't have, but I can make some realistic assumptions about what that probably should be, and then feed everything into the model so we can make predictions into the future. Is this going to be a crime? Yes or no? And then what kind of crime? And then what's the probability of that crime occurring? Again, it's not 0, it's not 100%, it's something in between. So we have the model here. We have the hour, weather, event density, day of the week, and borough, and so on and so forth. That gets fed into here. So that goes into model. We are label and coding all the elements in the model. So anything that is numeric, we can report on that using a classifier model or a random forest, or not random forest, or a regressor model. There's a bunch of regression models, right? Like at least 40, maybe 43 or 44 by now. So everything has to be encoded if it is a label, or has to be label encoded or one-hot encoded, or what's the other? Or I think feature encoding. I did a video on that a while back. There's 3 different types primarily that we use, right? So I like one-hot encoding, label encoding, and sometimes categorical encoding. That's it. So we'll have to encode everything. We're going to feed that into the X variable. So these are going to be the independent variables. So Y is the dependent variable. That is the label. That's what we're trying to predict, right? So everything over here is independent based on all these assumptions right here. We're going to get dummies and do label encoding, convert that to numerics, and feed that into the independent X variable, right? With all of these mixed in this blender, We're going to take all that information, look at the historical events of crime, and then try to predict into the future the Y variable there. Is there going to be a crime committed? Yes or no? And if there is a crime, what is the probability of that crime? Again, it's not really binary. It's not just yes or no. If there's no crime, then there's nothing. But if there's a crime, what's the probability of that crime occurring? Okay, so we're using the calibrated classifier CV again. Remember I told you I tested a few different classifiers, the random forest classifier, the log regression model, which is actually a classifier. I thought that would perform pretty well. It kind of was a little funky in making predictions, but I found the calibrated classifier CV, which is a cross-validation model. So it cross-validates everything. So it bakes in all these different scenarios, cross-validating all the scenarios across all other scenarios. So you don't somehow just pick a subset of data that represents the whole population if somehow you just perfectly pick the wrong records for your analysis, right? Cross-validation eliminates all these possibilities of accidentally picking the wrong records because it picks everything. It just folds everything together until everything is mixed in comprehensively. So we have the crime density. That is a new feature that we're adding to the data frame. We have the day of the week, the neighborhood, and the borough. Okay, we're going to encode all of these features. Move down here is the crime probability, and that comes from the calibrated model. If you go back here, calibrated model comes from over here. So the first thing we're doing is calling the model. Then we fit the model on X train and X Y. The X train comes from over here, right? This is the training set. This is the Y training set. So you have the independent training set and then the dependent. Again, Y is dependent, X is independent. Fit the model. Once it's fit, we're making predictions and we're looking at the predicted Y and seeing how close that matches to the actual test variables. So you have the training over here. This is going to be about 70, 75%. By default, I think it comes into, oh, here it is. Test size is 0.25. So the test right here is 25% of the population. This is going to be 25% of the population. This training right here is going to be 75% of the population. So remember, with machine learning, you have the training, you have the testing. The training is kind of like a student going to college. The training would be reading the book, going to the lecture, doing all the homework. The test is the test, right? How much did you learn during the training phase, and how do you regurgitate that information during the test? If you get an A, then you learned a lot. If you get a B, you learned some things. If you get a C, you didn't learn quite as much. If you get a D or F, you have to reevaluate what you're doing there, okay? So you didn't learn too much. So that's how this stuff works. And then the calibrated model is used to make the prediction. So we have the predicted probabilities right here. This comes from the encoded features, right? The independent features that we fed in, I just explained that. Then we look at how well the model is performing. So in this case, we only had 500 records, kind of a small subset of the population. Because all those things take so long to run, this would take the entire day to run all these scenarios. So that's why I picked 500. If you go back here and look carefully, we started with, I think, 75,000 or so. Where is that? 500. Let me just search for it. Up, I think. Yeah, so here we print the shape of the data frame. We had 71,242 records, but I cut it down to 500 and took a random sample of that 71,000, right? Right here, taking the random sample, because for me to analyze 71,000 is just going to take way too long, right? But if you take a random sample, it should be fairly representative of the population, and it's just going to run way faster than doing every single. Don't even tell me this thing is skipping yet. Okay. Yeah, I think I still haven't made a single penny on YouTube. I've been doing this for a year. I think when I actually get paid, if I ever get paid from these guys, I'm just going to buy a new computer. That's going to be my first investment here, because this thing is just getting ridiculous. Okay, so we have the map. Everything's done over here. So if we zoom out, we can see the red circles. Red comes from higher intensity of crime. If the crime probability is greater than 0.8, then orange. Color red if greater than, okay, so red if greater than 0.8. So anything that has a higher probability of 0.8, it becomes red, otherwise orange. So we have red or orange. Orange indicates there could be potential crime, not as high as the red. That's going to be 0.8 and higher. So it says 8. So there's the cutoff. There's 78%, this is 90%, 90%, 90%, 90%. So if we zoom in here, we see that there should be 90% chance of crime at the base of, this looks like the Brooklyn Bridge, right? Oh no, this is the Manhattan Bridge, okay. So this is the Manhattan Bridge. That looks like crime 90% down here on Wall Street. Well, those guys are just criminals anyways, right? So that's almost 90% because there's some investment banking, insider trading activity going on. So that's high crime. And then crime probability is 85% down here. And that is, what is that? I can't see because it's straight on top of that building, some kind of plaza, some kind of plaza. So again, probably white collar crime. So that's it. So it's pretty accurate what this classifier can do, right? It's predicting the probability of a crime, but there's a couple things that are not so desirable. Like, I don't know the day of the week, the time of the day, or what the potential crime could be. Could this be petty larceny? Could this be like breaking and entering? Could this be a violent crime? We don't know yet. So we have to go back and get some more information and replot the coordinates on the map. Okay, so in the second pass here, we're going to add in the type of crime expected with the probability, hour of the day, and create more granular detail about our crime forecasting tool that we just created here again. So we have the encoded data that I'm feeding in. This comes from the dummy data, hour of the week, weather, event, day of the week, so on and so forth, right? These are the independent variables. The crime type, that's what we're trying to predict. That's the dependent variable. We have the train test split again, and now we're going to replot everything based on the crime probability. Okay, so you have color red if greater than 0.8, otherwise orange. So we have that, but we're also adding in the hour of the day and the probability of the crime. And I think that is it, okay? Crime probability, hour of the day, and then, oh, I think that's it. Okay, well, let's take a look and see what this thing came up with. So if we go back here, you see crime probability, 79%. Type of crime, so most likely it's going to be an assault or related offense, 28% confident, and petty larceny, 16%. So if you add those together, 8 and 6 is what? 8, 9, 10, 14, 2 and 1 is 3, 4. So like 44%, I think 44%, give or take. But then like 66% chance that we don't know what the crime is going to be, and the overall crime probability is about 79%. So again, we can get within certain thresholds or certain probabilities here without making like a definitive declaration that there will be a crime occurring here. Okay, so here we have crime probability 90%. Now this is not a good neighborhood. Bedside is rampant with crime, so this totally makes sense. Crime probability 9%. This again is larceny or robbery. So if we round up to 30%, this would be 44% minus 1, so 43% chance of those two crimes occurring, and 90% chance of crime overall. Time of day was listed as 0-100. Now the time of day is listed at 1 a.m. in the morning. This is 1 a.m. Miscellaneous penal law, I'm not sure what that means. Petite larceny, 15%. Add those two together, it looks like 32%. And crime probability overall, some kind of crime, is 90%. But the breakdown between these two specific types of crime is about 33. Is that what we said? Okay, let me just look at one or two more. This is my neighborhood over here. There's actually nothing going on. This is where my son goes to school. This is Greenpoint. That's not the actual school. Oh, this looks like the Newtown Creek wastewater treatment plant. So I can't say for sure there's a crime in that specific place. It looks like it's inside the building, but I think that's what the KDE estimation is doing, is taking crimes from pretty close to that area and then picking one spot, right? So the KDE is not perfect, and you can't say with 100% confidence that there is going to be a crime in this latitude, this longitude coordinate, or this cross section of a couple of streets in Greenpoint or in Brooklyn or whatever you're looking at. But you can get pretty close, right? So the KDE process can be off by a little bit, but again, it's leading us in a direction where we know that there's probably going to be a crime, and it's taking us close to the point, and it's giving us the probability of the crime, and then breaking it down into a couple different categories. So here we see 75% chance of crime. This looks like Astoria, 24% and 19%. So this looks like if that was 20, that would be 44 minus 1 is 43%. Between those two, 75% overall in time of day, 1 o'clock in the morning. That one is 1 a.m. This is 0, 100 hours. So we should get that time thing fixed. This is 1 o'clock, 0, 100 hours. But again, it wasn't in the original data, so I had to make that up, right? Just to get something working here, just to get something. So a lot of these are 1 a.m. Just don't be outside at 1 o'clock in the morning. That's the message I'm getting from this, okay? Most of these are 1 a.m. But you can see that's 1 a.m. But you can see I did try to add in something for the hour HOVR. Let me go search for that again. And that comes from, let me see, go up here. But there was one other thing, like time or something. Where did they actually introduce that? Rand. Let me look for this. Okay, it's going to be one of these, right? So event density, social sentiment, hour. Down here, maybe. Oh, so not seeing it now, but I did add in the hour somewhere between 1, 2, and 3. Okay, well, if I can't find it in a couple seconds, I'll just give up. You don't see it. An hour and see it there. Come up with a better naming convention for this stuff. You don't see it. Oh, there it is. There it is. Okay, yeah. So these are the hours I came up with. So I tried to add that into the model, right, to have some context and some ability to look at the time of the day, because that's important too. If you just say 90% chance of crime, like when? Is that tomorrow? Is it today? Is it next week? Is it going to be on a Monday? Maybe a Tuesday, maybe a Wednesday. That's helpful, but Tuesdays and Wednesdays and Mondays are 24 hours long. Like what hour? I need more information, more context here of historical events so I can make predictions into the future about future events, right? So that's the context here. And there were assumptions, right? There were assumptions made. I tried to make it as realistic as I could. More data is better. The data set was okay. Comes from New York City. I haven't seen fantastic data. I don't think I'm going to do any more analysis on New York City data. It's kind of lacking, right? Like I wish I had hour in there. I wish I had more information. You can see 80% of the lat long coordinates weren't even filled out, right? The more data you get, the more you can feed into the model, the better decisions the model can make. If you're missing 20% of your data, I mean, you can impute missing data. There's machine learning techniques where you can like make a pretty accurate estimate of what that data should be. But do I really want to be estimating latitude, longitude coordinates for crime? Probably not. Like I want the real one. That's why I eliminated anything that doesn't exist, right? If the data frame has latitude, longitude coordinate of 0, I'm not even looking at these, right? Because it's not going to help the model. But it's a missed opportunity too. If we had 20% more valid features here, or not features, rows here that we could feed into the machine, make more accurate predictions. We're missing 20% and we're missing the time. So the analysis, I think, is pretty solid, but could be better, guys. Could be better. So now in this last example, I'm overlaying actual crime. This is blue. The actual crime is blue. We have official historical crimes. And then the red is the prediction, and the orange is the prediction under 80%. And the red would indicate over 80% confidence. The model is 80% confident in this prediction of the crime. So coming up to the end here, we're looking at skewed distribution of crime intensities using the calibrated classifier and cross-validating everything to avoid overfitting. So that was the basis for the analysis here. So this can play an important role in crime prediction when you want your predicted probabilities to be accurate and trustworthy. That's what we want. Otherwise, what's the point of doing the analysis, especially in high-stake applications like public safety, resource allocation, and recidivism risk assessment. So recidivism is kind of a big word. I heard this on, I think on the David Letterman show years ago. If you had a criminal past and you reformed and you don't resort to a life of crime. I think it's called recidivism, or that's the opposite. Like you have been exposed to crime and you have self-corrected, or you did not self-correct. It's one of these. The tendency of a convicted criminal to reoffend. Okay, so recidivism, you commit one crime and you commit more and more crimes, even after conviction, after you've been caught and slapped into the booty house. You go back to a life of crime, right? If you've reformed, I guess reformed is the opposite of recidivism, right? If you're reformed, you committed a crime, you were convicted of the crime, but now you don't engage in any more crime. Recidivism is the opposite. Convicted of crime, you committed a crime, you were convicted, and you go back like a dog returns to its vomit. It says this in the Holy Bible. The criminal returns to a life of crime. Okay, so I have some other things in the notes here. Random forest XGBoost, no need to assume distributions, but these models tend to be weak in terms of predicting crime because they can overfit for noise, especially with imbalanced data labels. That's what I found initially. Handles complex nonlinear interactions, outputs uncalibrated probabilities, fast to train and good default accuracy, but less interpretable, right? These are kind of black boxes. It makes a lot of assumptions and you just have to take it for granted, whatever the model is telling you. With the calibrated classifier, CV, again, which is short for cross-validation, it's much more interpretable, right? You can understand what the model is actually doing. And we see here, we can use categorical variables directly, but they may not extrapolate well in rare events like crime. Crime is kind of a rare event. It could be a lot in New York City, but overall, New York is a pretty safe city. And I think it's the safest, largest city in the United States, for sure, maybe in the world. Maybe, let's see. New York is going to be one. I can pretty much guarantee that. Large population, Irvine, California. I didn't know that. Okay. San Diego, San Jose, New York City. Despite its large population, New York has seen significant drop in violent crimes. So there you have it. So violent crimes are pretty rare. I mean, it so happens it's a big city. There's a lot of stuff going on here, but overall, it's a pretty safe place to be. Okay, so that's it, guys. That's my analysis. I'm going to wrap it up here. I'm going to save a copy of this and share this code with you guys. So you have all the code. You can copy and paste it. You have the data set. You can feed in the data set, do your own analysis, fiddle around with some of the inputs, check the outputs, and learn from the experience. That's why I put the videos together, for a learning opportunity for you guys. Okay, so that's it. I'm going to wrap it up here. Thanks so much for your time, and I will see you shortly when I record the next video. Thank you, and goodbye. Bye.